Thank you. First, I would like to thank the organizers for this very nice invitation. My name is Hao Ge from Peking University. I have two different affiliations in Peking University. One is the Beijing International Center for Mathematical Research. The other is the Biomedical Pioneering Innovation Center. In my group, we did research of combining mathematics, physics, and also biology and statistics. One part of my research is stochastic process-related mathematics and stochastic thermodynamics, and also single-cell kinetics. And very recently, we start to do statistical inference of single-cell data analysis. So I first want to very briefly introduce one of our works last year. And we studied the fluctuation theorem and thermodynamic inequalities for process stopped at stochastic times. For example, if you have a stochastic functional, which is can be a thermodynamic quantity, ft along the trajectory, and if you put on the shoulder of the exponential, take average, it can always be equal to 1. It is called a fluctuation theorem. And from this, you can derive the inequality, that is the average of ft is always non-negative. And then we can prove that you can always add a compensate term, delta t, which is very simple, which has a very simple expression. And you add them together, you will find out that this functional can be a martingale. Then you apply the martingale theory, you can arrive at the stochastic stopping time fluctuation theorem. That means at any stopping time, which is stochastic, the average of this term is always 1. Then you also do the inequality term. You can find out that the average of ft is not only non-negative, it can be greater than a term which is non-negative, which is sharpened than the original ones. We did this work actually after the interesting work by several other authors who is also in the audience, and we generalized their work to general thermodynamic functional and also general compensated term, and also we derive general thermodynamic inequalities and equalities. Then we go to the main story of today. So this is a story about HIV. HIV is a very famous virus which can infect a T cell. When the T cell is infected, it can have two different states. One is called a latent state, the other is called active state. So when it is activated, it can harm the human body. So if we zoom in and look at the genome of this virus, you will see there is some promoter called LTR, which controls the transcription and translation of a protein called TAT. And then there is some positive feedback. That is the main components of the this genome of this virus. And the people have already measured the stochasticity of this virus, especially this protein. You can see actually the noise, which is measured by the CV square, which is much greater than other human promoters. That means this virus is very stochastic. Then people also found out that if you measure the distribution of the copy number of this protein TAT, you can see it always has this bimodal distribution, which means it has two states. One is a very repressed state. It's corresponding to the latent state, which is very active state. So what is the mechanism behind this two different states? That is the problem. There are two different ways to answer this problem. One is using deterministic model. If you use deterministic model, you will find out that you need a parameter called Hill coefficient. That is quantify the degree of this positive feedback. If this one is 1 or less than 2, you can hardly have this bimodular distribution. Unfortunately, in experiments, they have measured this quantity, which is almost 1. So there is no such called deterministic bistability. If you do not account for this stochasticity, then you cannot explain the mechanism behind these two states. Then they measured the duration time of the two different states of the promoter, that is LTR. LTR can be very active, can be very inactive. It can stay in one state for almost 1 hour or more than 1 hour, then jump to the other state. So that is very slow transition between them. This such a slow gene state switching can result in such a bimodular distribution. Until now, everything is already known before maybe 10 years ago. So our interest has been caused by this science paper in 2014. They have proposed a new combined HIV therapy. They actually scan almost all the FDA-approved small molecule medicine. They scan them to measure two things. They put this molecule into a T cell, and also this T cell is affected by the virus, and you measure the copy number, the random copy number of this TAT number, and you can see there are two different categories of this small molecule. One is very traditional. That is the mean number of this TAT protein has been increased much, but the noise decreased a little bit. Then they found out the other categories called noise enhancer. That is the mean value does not change much, but the noise increased significantly. So as a summary, you can see you put the drug into this affected T cell, and you measure the GFP, that is the number or copy number of this TAT protein. You can see the first one is this one is untreated. The green one is the activator. It increased the mean, and this is a noise enhancer. That is the mean is unchanged, but the noise is significantly increased. And they want to know whether these two kinds of molecules, if you combine them together, is there any effect or drug synergy on the treatment of the HIV? And they found something very interesting. You can see actually the left one, on the leftmost, is one single activator. Then they add other noise enhancer in. So they combine one activator with a single noise enhancer. They measure all the combinations. And you can see once you add a noise enhancer, the effect of the drug, that is a percentage of the reactivation of this virus, because their strategy is to, if we add the small molecule that can trigger the latent state, the T cell, to be the active state T cell, and the active state T cell can be killed by the drugs. So why we cannot kill the HIV now completely? That is because the people who has affected the HIV can have some T cell that is in the latent state. Then once it being activated, it will have some damage to the human body. So you can always have some medicine every day. But if you have some small molecule drug, can trigger more percentage of the cells to be reactivated, then the drug can kill them to a more degree. So they found out that once you combine the activator and noise enhancer, you can significantly increase the percentage of reactivation of the cell, and can even up to 20 or 25%. And on the other hand, there is also some small molecules that can called noise suppressor. That is, the mean does not change, but the noise level decrease, and it has opposite effect on the percentage of reactivation. So there is a puzzle. If you have the activator, it can already have some reactivation ratio. Then if you add them together, activator and noise enhancer, it can increase much. But if you only have this noise enhancer, there is no effect. So we want to know what is the mechanism behind this observation. So we first choose a well-established model from a Cell paper. They have this model that is a two-state of this promoter. One is on and one is off. When it is on, it can transcribe and translate it, and there is a weak positive feedback. Then you can add an activator and a noise enhancer in. So we adapt the assumption from this science paper. They assume that the activator can directly increase K on, but the noise enhancer only can simultaneously decrease K on and K off. That is why that does not change mean, but increase the noise level. And when you put them together, they assume the activator can completely kill the effect of the noise enhancer on this parameter K on. That is their assumption. So we use a parameter we call F inhibition to characterize the degree that how the activator affected the noise enhancer. When it is equal to 0, that means the activator does not inhibit the noise enhancer. When it is equal to 1, it means the activator completely inhibits noise enhancer. And we use almost all the parameters, the same parameters from their model. And we found out there are two necessary conditions for the strat synergy. One is that the K off, that is the transition rate from the on state to the off state, it should not be very, very slow. They use the parameter 0.01, that is incorrect. If you increase this parameter, you will find out that it can have some strat synergy. That is one necessary condition. The other is most important one is that you should have this F inhibition equal to 1 or close to 1. That means the activator should kill the effect of the noise enhancer on this K on. So until now, use this two-state model, you can already explain the strat synergy, but it still seems to be a mystery. That is why the activator can stop the effect of the noise enhancer on this K on. Because in experiments, they use various different combinations of activator and noise enhancer. If you assume every pair they have direct interaction inside the cell, it sounds like a very strange assumption. So we want to know, is there any general phenomenon or general mechanism behind that? So then we adapt a four-state model, which is also very natural to modeling such a process. The LTR is the promoter of the HIV virus. When it is black, it means it is in the off state, without the combination of this polymerase. And when it is on, it bound with the polymerase and started to transcribe and translate it. So the green one, the green arrow, is affected by the activator, and this red one is also is affected by the noise enhancer. And also, because we have four states, there is two different kinds of models. One is under detail balance. The other is have some energy input or energy dissipation. Then the downstream of this model is similar to the previous one. When it is in the on state, it can transcribe and translate it, and there is some positive feedback. That is not the very crucial one of this model. So first, with detail balance. That is the simulation result. You can see there is no strat synergy. And also use mathematics and physics, you can prove under detail balance, no matter how complicated model you use, there is no synergy at all. And also in this four-state model, we can combine the black one into a single state, combine the red two state into a single state. We can calculate the effective F inhibition parameter. You can see in the detailed balance model, always 0. That means there is no drug synergy. That is consistent with our two-state model. And then when we break their detailed balance only through a single transition, we add a parameter E to the power beta into a single transition rate. Then you can see we can always have this drug synergy, no matter it is a little bit increase or significantly increase the result. And also we derive mathematically, we prove a theorem that is if the flux, the probability flux, which means if it is not 0, it means it does not in the detailed balance. When the flux is positive, that means it's clockwise, the direction is clockwise, then if and only if it's equivalent to, that is the drug synergy. So the drug synergy exists only and if and only if the probability flux is clockwise. If it is anti-clockwise, then every effect will be reversed. But the last problem is that, so we can explain the drug synergy using a general mechanism, but how can we explain this stronger one? Because in our previous simulation, it seems like the drug synergy is a little bit not that strong. So previously, we only added energy into a single transition rate. Then we found out that if you want to have a very significant synergy, that means you should have very strong probability flux. And also, that means if you from the off state to the on state, you will always choose from the right transition, go up to down. Then if you want to go back from the on state to the off state, then you always choose the left transition. Then this one, although this transition from the LTR to LTRP is also affected by the noise enhancer, but because we never choose this transition, so this effect has been completely stopped or almost stopped. So enlightened by this, we divided our energy into two parts. Beta 1 is added to this transition, and beta 2 to stop this transition. Their summation does not change. Then we tune beta 1 or beta 2. You can see we have some optimal drug synergy. And also, if you use the real simulation to mimic the experiments, you can see when beta 1 is greater than maybe 3, the reactivation percentage does not change much. So we combine this together and we choose very randomly choose beta 1 to beta 2 always equal to 5. That is not in the optimal value, but it is significantly to explain the results. In this way, we can increase the reactivation percentage from the activator to activator add with noise enhancer even double. And also from the right one is the reactivation rate, and the left one is we call P on, that is the percentage of the on state among all the state of the promoter. And also, if you combine the red state into on state, the black state into off state to mimic a two-state model, you can see the effective parameter of F inhibition is always 1. That is also consistent with our previously two-state model. And then as a last step, we want to know whether our new model consistent with all the previously experiments with using this HIV virus. We do not want to have some situation that is our model is conflict with some previous experiment observations. But luckily, all the previous results can be reproduced by our model. So this is a summary. we uncovered two necessary conditions for this noise-induced judge synergy. And also we propose a four-state mechanistic model with more state to explain why the energy dissipation is necessary and also very essential for this judge synergy. And also we properly breaking the detail balance, not only the quantity, but also the direction can be able to generate strong synergy. That is our work with my colleague, Professor Lei Zhang, and also Dr. Xiaolu Guo, and also two of my undergraduate students, Tang Tao and Xuan Duan. That is already published. Thanks a lot.